Hi Year 11s and welcome to this video on electron configuration. This is something you have done in the past, but we're going to be talking about a bit of a different method of electron configuration. We're just going to be going by the system in case you're wondering what should be noted and what shouldn't. This particular video, I'll be talking about quite a bit of background things that is just to help you understand what's going on, but it's not things that you necessarily need to know. It's more probably a bit higher level chemistry. So when I want you to copy something, there'll be this symbol next to the heading, the little C with a circle around it, and if it doesn't have that, then you don't need to worry about copying it. But I'll make that clear as we go along. So let's get going. So as you see, no C, don't worry about copying this, but this is just to show you the relative size of things that goes on. So if we're going down from a man, a human, at about 6 foot, down to a golf ball, which is quite tiny, down to a housefly, we're getting tinier and tinier. We're going down here to dust mite length, 250 micrometers. Now you can no longer see things, red blood cells, E. coli battery. Then we go down into nanomaterials and nano shell, which again you wouldn't be able to see. We're going to talk about this later. We keep on going, and this is still only 10 to the negative 7, a nano shell. But as we keep on going down, we get to a nanotube. We're at 10 to the negative 9. We keep on going, and at 10 to the negative 10 meters, or 0.1 nanometers, we get the hydrogen atom. So tiny. Minuscule, just to give you an idea of what is the size of the things we're talking about. So when we're talking about electrons and electron configuration, you would have talked about or heard about the model of an atom, where you've got the nucleus, you've got shells around the nucleus, and you would have also learned about how to write electron configurations. So for example, if I said potassium is 19K potassium, so it's got 19 electrons, and you would have gone, well, it's got 2, 8, so draw in my 8, and 1. That's how we would have done it in the past. 2, 8, 8, 1. And that's called a main shell electron configuration. But we're going to move on from that and talk about a more accurate model of modeling what's actually going on with atoms. So that's called main shell electron configuration. Again, not something you really need to copy down, but you'll probably remember that from last year. Remember that everything we're talking about is models. It's models of what we think could possibly be the way that atoms and electrons behave, but it's not set in stone because we don't know. We can't see atoms and we can't see electrons. Well, we can see atoms, but we can't see electrons. So this is just a model of how we think things are happening. So we've got shell number here, and we can go by this rule that the number of electrons that shells can occupy in each shell is given by the rule 2n. 2, it says 2n2 there, it should be 2n squared. Okay, again, you don't need to copy this yet, there's none of this sign. So what does that mean? Well, shell number 1, the maximum number of electrons is going to be 2 times 1 squared, which is 2. Shell number 2, 2 times 2 squared, which is 8. Shell number 3, 2 times 3 squared, 3 squared is 9, so that's 18. And shell number 4, 2 times 4 squared is 16, so that's 32. So this slide is just showing what we talked about on the previous slide, and you can actually write this slide down now, copy this one. So we get the maximum number of electrons in those shells, remember, by doing 2 times whatever the number of the shell is squared, which is where those values came from. So this would have been 2 times 3 squared, this would have been 2 times 4 squared. In case you're wondering what that is, that should be 2 to the n squared. So therefore this model of the atom over here is probably a more accurate model than what we talked about before. We've got the electrons in the middle, and then we have these shells where we've got actually 2 in that yellow shell, or the first shell, 8 in the next one, and 18 in the outside one. You don't need to draw that, but if you want to, you can. And then this slide here is just showing us therefore what the structure of those different atoms looks like. It's another way of showing the electron configuration, and by now I'm sure you probably remember doing these main shell electron configurations, so you could copy this. For example, for Mg, if I'm doing a main shell electron configuration, Mg is here, number 12, I would do 2, 8, 2. Very simple. Okay, 2, 8, 2, that's a terrible 2. So here's some facts we know. We know that the atomic number of each subsequent atom increases by 1. You've got your periodic table. As you move across the periodic table, your atomic number increases by 1, and that's mirrored by the increase of protons. Okay, so copy these points down. We know that atoms in period 1 have 1 electron shell. Atoms in period 2 have 2 electron shells. So you know, as the period increase the period number, and the number, I'm going to use hashtag for number, and that means that the number of shells also increases. Okay? And then we know that each atom in group 1 has 1 valence electron, group 2 atoms have 2, group 3 have 3, group 4 have 4. So increased period number, that means we're going down. That's point 2, but if this helps you understand that better, write this one. As we go across though, we increase the valence electrons, so that's going across. Okay? This one's not something that we have to copy, but just remember that these atomic shells are not perfect little shells like this. That's just a model, and really electrons orbit a nucleus in a variety of different orbits. They can go in dumbbell shape, they can go in different shapes. So don't be limited in your thinking by the fact that it's got to be in shells. It doesn't. Don't need that one. So now we're going to talk about a more in-depth view of electron configuration. So we have our shells, but within those shells we have things called subshells, and these are some dot points that it would be good to write down. Okay? So the maximum number of subshells is equal to the shell number, so e.g. shell number 4 contains a maximum of 4 subshells. And each subshell contains 1 or more orbitals. Now what is an orbital? It's a region where an electron can be found. And each orbital can hold up to 2 electrons. So now we've gone from simply having a shell to having a shell within a shell, so having 4 subshells. We go from shell to subshell, and then each subshell has orbitals. Okay? You might want to draw that just to help you think about this. This is a really helpful diagram to help us see what's actually going on. We're talking about shells and subshells and orbitals. How does it all fit together? This is shell 2. Okay? And remember we said that the number of subshells is equal to the shell number. So if we've got shell 2, that means we have a maximum of 2 subshells that can be allowed. So here's our diagram. Here's our shell, this big one. Then here's our 2 subshells. 1, 2. That whole thing is a subshell. Then within the subshell we have orbitals. Here's 1. Here's 3 p orbitals. Okay? You don't need to know these diagrams. You don't need to be able to draw them, but this is how it fits together. Shell, then subshells, then orbitals within subshells. Okie dokies. So what we've got going on here, and you might just want to copy this bit on the left hand side, is that the subshells actually relate to different blocks on the periodic table. So we've got the S block on here where the metals are, then we've got the D block, the transition metals, and then the P block, which is non-metals, and then we've got F block down here. So they are relating to different subshells. So then if we look at this table here, and you don't have to copy this table, but in shell 1, the maximum shell capacity, and that means that's talking about the electrons in this case, is 2, 8, 18 and 32. We talked about that before. Now we talked about the fact that the maximum number of subshells is equal to the shell number. So in shell number 1, you can have a maximum of 1 subshell. In shell 2, you can have 2 subshells, shell 3, 3 subshells, shells 4, 4 subshells. Now you'll notice that these subshells have different names. We've got the S, P, D, and F corresponds to this over here. And what they are describing, S, P, D, and F, are describing actually different shapes of your subshell. But when we have shell 2 and we have 2 subshells, our 2 subshells are 2S and 2P. When we have shell 3, our 3 subshells are 3S, 3P, 3D, 4, 4S, 4P, 4D, and 4F. Then we go on from the subshells, we actually go into the number of orbitals. So an S subshell has one orbital, a P has 3 potential orbitals, and a D has 5 potential orbitals, and F has 7. You do not need to know this, by the way, so don't stress. But each of these orbitals can hold 2 electrons. So that means in the S orbitals, in total you have 2. In the P subshell, you can have 6 because there's 3 orbitals which can hold 2 each. In the D, you can have 10 because there's 5 orbitals which can hold 2 each, etc. Again, just remember this bit on the left-hand side. Don't worry too much about the table, but hopefully that's helped you understand it a little. So this is just for interest, and this is the shapes of your orbitals. So here you can see the S orbital, it's nice and round. Your P orbital, remember we said you can have 3 different P subshell, you can have 3 different orbitals, and your D subshell, you can have 5 different orbitals which look like this. You don't need to know these shapes though. And then when we're doing electron configuration, we operate on the bounds of the principle known as the Aufbau Principle, where electrons are placed in the lowest energetically available subshell first. So they're placed where the energy is the lowest. Now that is actually closest to the nucleus. Okay, so that is closest. The most energetically stable one is the one that is actually closest to the nucleus. Apologies for my handwriting at the moment. Now remember, an orbital can hold at most 2 electrons. We said this. Electrons only pair up in orbitals once all orbitals of equal energy are singly filled. So what that is talking about is, for example, in the 2p. Remember we said in the p subshell you can have 3 different orbitals. So what would happen is that if we're filling electrons into that subshell, we'd fill into that one, and then that one, and that one, so we'd fill 1 into each orbital, and then we'd pair it up once we filled them up. Okay, so once each has 1, then we fill up the others. So the most stable arrangement of electrons in a subshell occurs when the maximum number of unpaired electrons exists. So it is actually more stable when you have a lot of unpaired electrons, when you don't have this thing happening. So that is why we don't pair it up. Alright, so we finally get on to actually filling electron orbital subshells and shells. So we talked about how the first electron shell, and please copy these notes, the first electron shell contains a single s orbital. It's the closest one to the nucleus. It fills with electrons first because that's the most electrically stable. So for example, hydrogen, it's got 1 electron, so that just goes in the 1s orbital. And so we write that as 1s1, actually write as 1s1, but put that little 1 as a superscript, so like that. Okay, 1s1. This little diagram here helps explain how things get filled. So firstly we fill the 1s, then we fill the 2s, then we actually fill 2p and then 3s, then we fill 3p and 4s, then we fill 3d, 4p, and 5s, etc. This is a diagram which you really need to copy and you need to know, because sometimes you'll go, well, what do I fill next? And you always go from that top corner downwards. Alright, so you go 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s. And that is because we do that because sometimes you actually fill an orbital in shell 4 before you fill one of the ones in shell 3. So make sure you've got this copied and you understand how it works. So moving on from hydrogen, which had 1 electron, we then go to helium. It's still in period 1, so it means it has 1 shell, but now it can fit, now because it's got 1 extra electron, we get 2 electrons in that s orbital, so it becomes 1s2. Lithium, on the other hand, has 3 electrons, so we're going to go 1s2, then we're going to go, what's the next one? Well, it's this one on the diagonal, 2s, and I'm going to put that 1 orbital into there. So what do these refer to? Well, that 1 there, this one, that refers to the shell. That's the main shell. And then the S refers to the orbital, the subshell, so an S subshell. So that's the subshell. And the 1 refers to the number of electrons within the subshell. Okay? Okay, so this is another way of looking at it. We start with 1s, then we fill 2s, then 2p, then 3s, then 3p, then 4s, 3d, 4p. Another way of looking at it, that diagonal shape that we talked about before. So let's do some examples. Alright, I'm going to just write that thing out here to help me. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, and then I'm going to put my arrows in. So that goes there, that goes there. In a test, I would strongly suggest that you did this, that you actually fill it out first. Okay, so let's do an example. Let's do calcium. Calcium is 20 Ca calcium. Now remember, you need to copy this, by the way. Remember our s orbitals. So s orbitals contain 2 electrons, p contains 6, d contains 10, f contains 14, but you'll never really need to go to f. Alright, so let's count. Start with calcium. I'm going to do 1s2. And I'm going to look at my diagram and go, alright, next one's 2. 2s2. Next one is a p orbital. P orbital can hold this one. So p orbital can hold 6 electrons. So 2p6. Next one, follow the arrow down. Next one is the 3s orbital. Again, can only hold 2. 3s2. I'm just going to add them up. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. Alright. So 3p is next. Is it? Yes, 3p is next. So I can put 6 in that 3p. So 3p6. What did I say I had? 12. 4s2. Now does that make 20? 4, 10, 12, 18, 20. Sure does. Alright. Let's pick another one. Let's pick 23. Scandium. It's off the top.